Picture this. It's early morning, the sky's still dim, coffee still steaming in your hand. You plug in your car, and exactly 5 minutes later, the battery reads full. Not 30 minutes, not an hour, 5 minutes, and then you drive off and don't need to stop again. Even on a trip from Los Angeles to Seattle, over 1,100 miles without a single charging stop. That sounded like science fiction to most people just a few weeks ago, because for years the consensus was that solid-state batteries, long called the holy grail of the EV world, were still at least a decade away from mass production. Too many unsolved problems, too many barriers, too many broken promises. Every year, analysts pushed the timeline back further. 2030 last year, 2035 the year before. The industry had basically stopped trusting bold claims altogether. Then Toyota spoke. Not at a flashy launch event with a glowing stage or a live stream watched by millions, just a closed-door meeting in Toyota City, Japan, with a few dozen senior executives, select investors, and engineers who'd spent a decade working quietly, no theatrics, no special effects, just numbers. And those numbers froze the industry. 1,200 miles on a single charge, a full charge in under 5 minutes. No cobalt, no nickel, no dependence on volatile geopolitical supply chains. Most importantly, this wasn't a lab prototype. It's a battery already road-tested under real conditions across 4 continents. And within 72 hours of the news leaking, more than $46 billion evaporated from the combined market value of traditional automakers and battery makers. Once hyped EV startups suddenly looked far less exciting, and major corporations across America and Europe quietly convened emergency meetings. The question is no longer whether solid-state batteries are possible, it's how Toyota pulled this off without anyone seeing it coming, and whether this is the real turning point or just another hype cycle waiting to deflate. To understand why this announcement landed like an earthquake, rewind about 3 decades. Sony introduced the first commercial lithium-ion battery in 1991, hailed at the time as a near-miracle compact, rechargeable, denser than anything before it, and within a decade it powered laptops, phones, cameras, and eventually electric vehicles. And an entire industrial ecosystem worth hundreds of billions of dollars grew up around that single chemistry, with supply chains stretching from cobalt mines in Congo to factories across South Korea, China, and the US. But lithium-ion has real limits, and after 30 years, they're becoming impossible to ignore. First, energy density. Today's best lithium-ion cells store around 250 watt-hours per kilogram, which sounds abstract until you realize it means an EV needs a battery pack weighing up to 1,000 pounds or more to hit 300-400 miles of range, making most EVs 500 to 1,500 pounds heavier than comparable gas cars, with real consequences for handling, efficiency, and cost. Second, charging speed. Even the fastest 350 kilowatts DC stations need 20 to 30 minutes to go from 20 to 80% under ideal conditions. And that gets worse in extreme heat, cold, or with an aging battery. Still a wide psychological gap compared to a 3-minute gas fill-up. Third, and less discussed but critical, is safety. Lithium-ion relies on a flammable liquid electrolyte, and when damaged, overheated, or punctured, it can ignite through thermal runaway, a fire nearly impossible to extinguish with water that can consume a vehicle within minutes, denting consumer trust each time it happens. Fourth is raw material supply. Cobalt mostly comes from the Democratic Republic of Congo, where mining has drawn serious human rights criticism, while lithium flows largely from South America's Lithium Triangle and Australia, and nickel from Indonesia and Russia. Supply chains running through unstable geopolitical territory that the entire industry has had to live with for 30 years, hoping someone would eventually find a way out. Toyota is rarely the name people associate with bold technological leaps, while Tesla dazzled with the Model S, Model 3, and Cybertruck, while GM committed to phasing out gas engines by 2035, and Ford poured tens of billions into new battery plants. Toyota appeared to be watching from the sidelines, still selling hybrids and insisting pure EVs weren't quite ready. Critics called it stubbornness from an aging giant. It was actually camouflage. While attention stayed fixed on Tesla and EV startups, Toyota was running one of the largest battery research programs in automotive history, thousands of engineers, billions of dollars, and one clear target: not improving lithium-ion, but replacing it entirely. The bet was on solid-state batteries. The core idea isn't new. Swap the liquid electrolyte for a solid material, and you immediately eliminate fire risk while boosting energy density and charging speed. The theory is elegant. The execution has been brutal. The persistent failure point has always been the interface between the solid electrolyte and the electrodes, since solid materials expand and contract unevenly at the atomic level, with the temperature changes eventually cracking after hundreds of cycles and degrading performance. The exact wall that stopped dozens of companies over 2 decades. Toyota didn't patch that problem, and they sidestepped it with an entirely new proprietary ceramic polymer matrix that combines the strength of advanced ceramics with the flexibility of organic polymers, producing a solid electrolyte that withstands thousands of expansion contraction cycles without cracking or losing conductivity. On top of that, they added a graphene-infused anode. Conventional graphite anodes and accumulate lithium ions during charging, and that over time form metallic dendrites, tiny branching structures that reduce capacity, cause internal shorts, and in worst cases trigger fires. Toyota's graphene anode nearly eliminates dendrite formation outright. In internal testing, cells survived more than 2,500 full charge-discharge cycles while losing under 8% capacity, translating to over 1 million miles before any meaningful range loss in real-world use. Together, these two breakthroughs push energy density from roughly 250 watt-hours per kilogram in today's best lithium-ion cells to nearly 450, almost double the energy in the same space and weight, while the resulting battery pack is 30% lighter and 15% smaller than the packs in Toyota's current BZ lineup. The most striking figure, though, is thermal behavior. Under extreme fast charging or heavy sustained loads, pack temperature barely shifts, something no commercial lithium-ion pack today can match. That cool running characteristic is what unlocks everything that follows. When a battery stays cool, you can push current into it much faster without damage, the basis of what Toyota calls its hypercharge system. For context, Tesla's Supercharger V3 tops out around 250 kilowatts, and Electrify, America's fastest stations, hit 350 kilowatts, currently the industry ceiling. Toyota's hypercharge system delivers 2.2 megawatts, roughly 6 to 9 times more powerful, and through a new liquid-cooled cable can take a solid-state pack from completely empty to completely full in under 5 minutes. Not the usual 20 to 80 marketing range, but true 0 to full. Naturally, the obvious concern is grid strain. If hundreds of vehicles plug into two 2-megawatt stations simultaneously, what happens locally? Toyota's answer is pairing each station with an on-site solid-state storage buffer that trickle charges continuously, and the grid throughout the day and discharges rapidly when a car plugs in, so the grid only ever sees a steady, modest load rather than the spike itself. On safety, Toyota has turned solid-state chemistry into a genuine differentiator rather than a marketing checkbox. In crash testing, punctured solid-state packs didn't ignite, explode, or release dangerous heat. They simply stayed intact. Under Japan's strictest fire simulation standards, Toyota's pack released less than 10% of the heat output of a comparable lithium-ion pack. Not an incremental gain, but a fundamentally different risk profile. Toyota has also integrated the battery directly into the vehicle's structural frame, a cell-to-frame approach that saves weight while boosting rigidity and crash protection. The resulting solid-state vehicle platform is 28% lighter than today's RAV4 while being structurally stronger. None of this matters if it can't be manufactured at scale and at a price people can afford. And this is where Toyota's story diverges sharply from typical battery startup hype. Two automated solid-state production lines are already running at the Motomachi plant in Japan, not pilots, fully operational, with initial capacity around 250,000 packs per year at a 91% yield rate, compared to under 70% for most rivals still in small-scale trials. Robots handle ultra-thin ceramic electrolyte sheets inside sealed, moisture-free environments and under AI quality control, tracking every micrometer, cutting labor costs per pack by roughly 60%, while doubling production speed and nearly eliminating human error. Meanwhile, a dedicated gigafactory is under construction in Thailand, built from scratch purely for solid-state production. With no legacy lithium-ion lines mixed in, Toyota's goal is for 80% of solid-state components to be produced domestically by 2027, creating a largely self-reliant supply ecosystem. The vehicle built for this platform already has a name, the Toyota X1, the company's first model engineered entirely around solid-state architecture from the ground up, over 1,200 miles of range and a 5-minute full charge, a starting price under $30,000, and thanks to cell-to-frame integration, lighter, stronger, and safer than any EV currently on sale. Some inside Toyota reportedly expected to surpass the Corolla as the company's best-selling model ever, an ambitious claim that starts to look plausible given the numbers involved. Of course, this all sounds almost too clean. So where are the caveats? Several, and they matter. First, the 200-mile figure comes from controlled testing, not everyday customer driving. Real-world numbers under EPA or WLTP standards typically run 15 to 25% below official figures once highway speeds, climate control, and cold weather factor in. Toyota itself has acknowledged that real-world range under mixed American driving conditions may land closer to 958 miles, still extraordinary, but not 1,200. Second, despite live production lines, scale remains far below what mass market demand requires. 250,000 packs annually sounds significant until you remember. Toyota sells around 10 million vehicles a year, and the Thailand plant will expand capacity substantially, but that's a multi-year ramp that could hit bottlenecks in skilled labor, specialized ceramic supply chains, and manufacturing learning curves. Third, the sub-300 X1 price hasn't been officially confirmed. It comes from internal sources and leaks rather than an official announcement, and large-scale ceramic electrolyte production currently costs more than conventional lithium-ion manufacturing. Toyota is betting costs will fall with scale and automation, but that remains a projection. Fourth, and perhaps most important, long-term real-world durability hasn't been independently verified. Toyota's 2500 cycle sub-8% degradation figures come from internal testing, which is always more controlled than messy real-world conditions involving uneven charging habits and extreme temperature exposure over years, and none of this discredits what Toyota has shown, but an honest account requires weighing both sides. The EV industry has seen plenty of bold promises arrive late or not at all. From silicon anode batteries to sodium-ion chemistry to affordable long-range EVs broadly, Toyota does have a stronger track record than most at turning lab breakthroughs into road-ready products. The Prius, launched in 999999999 and still sells well today, though that used already proven lithium-ion chemistry, making solid-state a considerably bigger leap. And Toyota isn't racing alone. In China, CATL, the world's largest battery manufacturer with over 37% of global EV battery market share, has its own solid-state program targeting commercialization by 2027, backed by enormous manufacturing scale, deep automaker relationships, and cost advantages tied to China's dominant raw material supply chains. Though CATL still relies on nickel manganese cobalt cathode chemistry, meaning continued dependence on cobalt and nickel, even with a solid electrolyte, something Toyota has eliminated entirely. In South Korea, Samsung SDI is partnering with Stellantis on solid-state development, but remains in small-scale testing rather than mass production. In the U.S., QuantumScape, heavily backed by Volkswagen and Microsoft, has announced breakthroughs repeatedly while missing timelines just as often, with its stock down more than 80% from its peak. Solid Power, working with BMW and Ford, is similarly still in pilot stages. What separates Toyota from this crowd is that it doesn't need to raise capital through an IPO or satisfy venture investors. Every quarter, it has roughly $250 billion in annual revenue, 70 years of manufacturing experience, and 2 decades of optimized hybrid battery production lines, a manufacturing foundation no startup boardroom can replicate. GM, Ford, and Stellantis, meanwhile, face an uncomfortable position, having committed tens of billions to next-generation lithium-ion plants like Ultium and Blue Oval City. Those investments can't simply be cancelled. Yet if Toyota's solid-state bet pays off, those factories risk becoming outdated before reaching full capacity, which is likely why Detroit's first reaction to the announcement was silence, followed by closed-door emergency meetings. Volkswagen, which once called its own solid-state program a top strategic priority, now has to reckon with a development timeline that suddenly looks dated. If everything Toyota has announced holds up, the implications stretch well beyond the showroom. An X1 launching around 2026, under $30,000 with real-world range near 1,000 miles, would undercut the Tesla Model 3 on price, while roughly tripling its range, directly addressing the 3 biggest barriers to EV adoption identified in consumer surveys: range, charging time, and price. Toyota has also indicated solid-state technology will expand into home energy storage by 2026, where a rooftop solar setup paired with a solid-state pack could power a household for nearly 2 days without grid draw, compared to under 1 day with current technology, meaningful for storm-prone regions or areas with high electricity costs. At a larger scale, Toyota is exploring grid-scale storage using the same architecture, which would be lighter, safer, and longer-lasting than today's lithium-ion farms, helping solve renewable energy's core storage problem. Toyota's aviation division is reportedly even evaluating ceramic solid-state cells for next-generation drones and high-altitude aircraft, where energy-to-weight ratio is critical. If 450 watt-hour density holds up long-term, medium-range electric aviation moves from speculative to technically realistic. There's a geopolitical dimension, too. Widespread adoption of cobalt-free, nickel-free batteries would pressure markets currently dominated by Congo and China, while Japan, lacking major natural resources, would gain real leverage through technology itself. And if Toyota scales solid-state production to millions of packs annually, it stops being simply a car maker and starts resembling a major energy supplier in its own right. So, stepping back, for decades, the EV industry has been boxed in by lithium chemistry good enough to start a revolution, not quite powerful enough to finish it, hampered by limited range, slow charging, fire risk, and fragile supply chains. Toyota didn't try to break through that wall. It built an entirely new road around it, a proprietary ceramic electrolyte, a dendrite-resistant graphene anode, and a 2-megawatt charging system that doesn't strain the grid. Automated production with industry-leading yield, no cobalt or nickel dependence, and a sub-300 vehicle meant to bring all of it to millions of buyers. That's the full picture if everything goes as planned. But the gap between proven in the lab and sold at scale has always been larger than expected in this industry, and real costs tend to exceed early projections. Toyota knows this better than most, having lived through it with the Prius and early hybrids, and the quiet, methodical way they've approached this rollout, testing across 4 continents and running live production lines before any major press event. Maybe the strongest signal yet that this isn't ordinary hype. Still, the real test comes over the next few years. Will the X1 launch on schedule? Will real-world range hold close to the claims? Will pricing land near $30,000? And will the battery still perform after years of actual use? No press release can answer that. Only time can. What's already changed is the nature of the race itself. The question is no longer whether solid-state batteries are achievable, but who masters them first. And Toyota currently holds a significant, if contestable, lead. What do you think? Has Toyota genuinely pulled the future forward, or are you still skeptical of these numbers?